So, as I mentioned, today's class is about the wave-like property of matter, like electrons or protons or neutrons. Like Tuesday's class was about the particle-like properties of photons, of light. So I'm going to start by introducing the idea, the notion, the concept of wave-particle nature of matter. Just like in the last class, we introduced the notion, the concept of the wave-particle nature of light. The fact that light has both wave and particle properties is peculiar based on our everyday experience. The fact that matter has both wave and particle-like properties is also peculiar based on our everyday experience. But actually, the fact that light and matter both have wave-particle-like properties is actually a joining together, a unification of our notions, concepts of matter and light. They're going to be described by the same sort of wave-particle properties, both for light and matter. Second bullet here, I'll talk about some evidence for the wave properties of matter. So we'll look at a very specific experiment, a very specific measurement that first demonstrated that particles like electrons have wave-like properties. And then we'll move on to the last topic here, which is that light has both wave and particle-like properties. That electrons have, or matter have, both wave and particle-like properties, leads to some important conclusions about the quantum world that are quite different from the sort of classical world. And the important conclusions are wrapped up in an idea, a notion called the uncertainty principle. The important conclusions are to do with, in classical world, we think in principle we could know everything about a particle. In quantum world, we believe that in principle you can't know everything about a particle. So in classical world, in principle, there's no limit on your ability to measure things. In quantum world, there is a limit on your ability to measure things. That's a fundamental difference between quantum and classical worlds that comes out of, that is a consequence of wave-particle duality, wave-particle nature of light and matter. Okay, better get on with this. First topic. So I called this unification of matter. It's really discussing matter and light. It's really discussing the fact that both matter and light have wave-particle properties, sometimes they act like waves, sometimes they act like particles. That's quite different from our classical description of matter and light. So our classical description of matter is that matter is made of little particles. They used to call them corpuscles. So little particles, and those little individual particles could carry energy and they could carry momentum. And so we imagine them as, electrons, protons, neutrons, as tiny little billiard balls that are carrying some energy and carrying some momentum as they fly around. Our classical picture of light, electromagnetic waves, was that it is simply a wave. It is a continuous and smooth wave of electric fields and magnetic fields that are oscillating and vibrating and interacting and sustaining one another. So that's our classical picture of light. This survived until the beginning of the 20th century. And then at the beginning of the 20th century, this is where this simple conception broke down. So what happened is that in the quantum description of light and matter, as opposed to the classical description of light and matter, in classical description of matter, particles had energy and momentum. In classical description of light, light has a wavelength and a frequency. Now, in the quantum description of matter and light, the light and the matter have both energy and momentum, act like particles, and they have frequencies and wavelengths, act like waves. So those distinguishing features of wavelength and frequency that we associated with waves and energy and momentum that we associated with particles now become blurred because light and matter both have those properties, those wave-like and particle-like properties. So you can associate wavelengths and frequencies with matter, which seems strange. You can associate energy and momentum with particles of light, which seems strange. So there's really this is a cartoon, but it's a joining together of how we think about, it's a synthesis of how we think about light and matter. They're no longer fundamentally different. They are a much stranger thing, but they're a common thing. Okay. As we talk about I called it here the granularity of light, so that's the fact that light comes in little packets or particles, and the fuzziness of matter. I'm calling it the fuzziness of matter because we'll see that matter is no longer these sort of point-like particles. It's sort of smoothed out in space and time. A key number arises, a key constant arises, is Planck's constant again. So this constant sets the scale of both the granularity of light, so the little packets of light, and it sets the scale of the fuzziness of matter, sort of the wavelengths and the frequencies of matter. So it does both. For example, suppose we could do this. We can't do it, obviously. If I was to take Planck's constant, so it is 6.6 times 10 to the minus 34 joule seconds. If I was to take it and turn it down, make it even smaller than it actually is, make it so small that it vanishes, what would happen? If I was able to do that, what would happen is the granularity of light would vanish, so the particle-like properties of light would vanish. It would just become a smooth wave. And the fuzziness of matter would vanish. The waves of matter, the frequencies associated with matter, that would vanish too. And we return to the classical notions of light and matter as either waves or particles, and not having wave and particle properties. So that's Planck's constant equals 0. If I was to turn, now I'm going to turn up Planck's constant. That would be really interesting. If I could turn it up from 6.6 times 10 to the minus 34 joules seconds, suppose I could turn it up to 6.6 joules seconds. So 10 to the 34 times bigger. If I could do that, then wave-particle duality, which seems so weird to us because we have no everyday experience of it, wave-particle duality would be part of our ordinary everyday lives. So you would be, partly a wave and sometimes a particle. I would be standing up here and sometimes a particle, sometimes a wave. Our universe, our world, our experience would be completely different if we were able to jack up Planck's constant to be a size scale of everyday physics. So it's really this number that determines the fact that in our everyday lives we see things as light and matter as particles and waves, but at the microscopic level of atoms, molecules, subatomic particles, electrons, protons, neutrons, then at that level, things like light and matter exhibit both their wave-like and particle-like properties, because that's the scale set by Planck's constant. Okay, so now we want to get a bit more quantitative. Like we met some equations, or equation for the particle-like properties of light, we're going to meet an equation for the wave-like properties of matter. Okay, and this equation is due to de Broglie. This is quite a name, I think. I can't even imagine reading it to you. But everybody just calls him de Broglie because his first names were so many and so long. He, a little bit jealous of this. I think this is I'm a little bit resentful of this. So he wrote his PhD. It was 3 pages long, not 200, 400 pages. It's 3 pages long. And then he got a Nobel Prize for his PhD. So that was quite a successful PhD. And it was simply a PhD based on an idea, a notion, a hypothesis that like light, a wave, has particle-like properties. He hypothesized that matter, particles, also have wave-like properties. And he wrote down an equation for the wavelength associated with these matter waves. So he was the first person to explicitly write an equation for the wavelength of matter waves. Okay, so over here on so again, this is going back to a quantum description of matter and light. Matter's on the left and light is on the right. And we talked about light last class, and I think this was the key equation. That the energy of the packets of light, so that's the E here, is determined by the frequency of the light waves through Planck's constant. That's the H here. So E equals Planck's constant times frequency tells us the granularity, the quanta, the photons of light. Here's de Broglie's equation, sort of the partner to this equation for matter waves. So this equation tells you the wavelength of the matter waves. That's the lambda here. So if there are matter waves, they have a wavelength. They have a characteristic wavelength. And it tells you what that wavelength is in terms of, now it's the particle-like properties of the matter waves rather than the wave-like properties of the light. It's the momentum of the electron or the proton or the neutron. That's the P in the denominator here. And to get the wavelength, corresponding wavelength, you just divide Planck's constant by that momentum. So these two equations play very similar roles in the what we call the wave-particle duality of matter and the wave-particle duality of light. So they're the bridges between the particle properties and the wave properties. On one side of those equations is the wave properties, and the other side of the equations is the particle-like properties. So for the matter waves, for example, on one side you see the momentum, that's a particle thing. On the other side you see a wavelength, that's a wave thing. For the case of light, on one side of the equation you see the frequency, that's a wave thing. On the other side you see an energy, that's a particle-like thing. And the bridge, again, is through Planck's constant. Without Planck's constant is setting the scale of the connection, the relationship between the wave-like properties and the particle-like properties. Actually, really, I'll just mention this. I don't want to go into detail, but this equation here is really just a version of this equation here. The energy in the case of light here can be written in terms of the momentum of this is the energy of a photon. It could be written in terms of the momentum of a photon. The frequency over here, this is the frequency of the light, that could be written in terms of the wavelength of the light, just through frequency times wavelength equals speed of light. If you do that, what you discover that this equation here is also P equals Planck's constant divided by the wavelength. And that's this equation over here. So these really are the same relationships between the momentum, a particle-like property, and the wavelength, or a wave-like property. Okay, so this tells you how long ago I made this slide, like 100 years ago. But anyway, you might be thinking, right, well, I don't think I believe that particles have wave properties, right? When I play basketball, or I play soccer, or I play football, God forbid, I don't experience the wave-like properties of the basketball or the soccer ball or the football. They just seem like particles. So how do we reconcile the fact that in our everyday life we don't experience the wave-like properties of matter that I'm claiming? So the key thing is that a basketball, a football, a soccer ball do have their matter, but they do have associated wavelengths, but their wavelengths are too small, far too small for us to observe the effects. And so that's what this example calculation is about. I'm calculating here on this slide the de Broglie wavelength of a basketball. And then on the next slide, I'm going to calculate the de Broglie wavelength of an electron. So I'm going to calculate the de Broglie wavelength of an everyday object, and I'm going to calculate the de Broglie wavelength of a subatomic particle, an electron. We're going to see why, when I do those two calculations immediately, why I don't need to worry about wave-like properties of matter for basketballs, soccer balls, footballs, but I do need to worry about wave-like properties of electrons and protons or neutrons when I build an atom from the electrons, protons, and neutrons. So in this example, I've got a basketball, and apparently its mass is 0.6 kilograms, and apparently speed is 10 meters per second. So maybe that's typical of, maybe that's right for a basketball, maybe it isn't. And maybe that speed is right for a basketball, maybe it isn't representative. But these are everyday numbers, right? This mass and this speed. So let's calculate the de Broglie wavelength of our basketball, 0.6 kilogram basketball traveling at 10 meters per second. To calculate the de Broglie wavelength of the basketball, I want to know the momentum of the basketball particle, because that momentum of our basketball particle leads to the bridge between the particle-like properties of matter and the wave-like properties of matter. So I'm going to first just calculate the momentum. Well, that we know how to do that. We just multiply the mass by the velocity, so it's 0.6 kilograms times 10 meters per second. That's 6 kilograms meters per second are the units. Or this is going to be a handier way of expressing the units. We don't normally write it like this, but you can rewrite the units as joules seconds over meters. This is also a unit of momentum, just like this is a unit of momentum. It's just a different way of expressing the units of momentum from this familiar way of expressing the units of momentum. You'll see why I use that in a moment. Okay, now that's the familiar sort of 211 calculation of a momentum of a particle that's traveling with a certain speed and owns a certain mass. Now we're going to calculate the corresponding wavelength of the matter wave associated with that particle with that particular momentum. So that's where we use de Broglie's equation here, that the corresponding matter waves for the basketball have a wavelength that's determined by the momentum of the particle and Planck's constant. And so all I've got to do is divide Planck's constant by the momentum of the basketball. So Planck's constant, again, 6.6 times 10 to the minus 34 joules seconds. The momentum of the basketball was 6 joules seconds divided by meters. That's the units for the momentum of the basketball. And if you do that calculation, you get this little result here. So this is 1 times 10 to the minus 34. It's going to be that scale, right? The Planck's constant was a scale of 10 to the minus 34, and we're dividing it by an everyday number, 6. That's the wavelength, 10 to the minus 34 of a meter for a basketball. That's why, basketball coaches aren't talking about basketball matter waves, because the matter waves are so small, they're absolutely completely unobservable. We can't detect the matter waves of an everyday object. We do believe that everyday objects have matter waves because our experience with subatomic objects, but we've never ever seen detected a basketball matter wave or an everyday object matter wave. It's just far too small. Okay. This would be the example of a case where the matter waves are important. So this is the same calculation. This is exactly the same calculation for the matter wave, not of a basketball of a certain mass and certain speed, but rather of an electron with a certain mass and a certain speed. So we're told in this case we've got an electron. The mass of an electron is 9 times 10 to the minus 31 kilograms, so it's tiny compared to a basketball. We're told that our electron has a speed of 1,000,000 meters per second. Now this is very fast compared to a basketball. This is quite typical of electron speeds in atoms. So that's why I picked this number. So if we want to find the wavelength of these matter waves, of these electrons with this speed, this mass, then we would calculate the momentum again. That's the particle-like property. And then we use de Broglie's wavelength formula to determine the matter wave's wavelength. So let's just do that. Again, momentum is mass times velocity. I'm just multiplying the mass of the electron by the speed of the electron. I get this number here. It's 9 times 10 to the minus 25. Again, the units are kilograms, meters per second. That's just the product of the units of the speed and the kilograms. Or I can rewrite it in this fashion here, which is handy for this calculation. So I take that momentum, and now I'm going to calculate the electron's matter wavelength. All I've got to do is divide Planck's constant, this constant of nature, by the momentum of the electron. So I'm doing that here. Here's the Planck's constant, 6.6 times 10 to the minus 34 joules seconds. Here's the momentum of the electron, 9.1 times 10 to the minus 25 joules seconds over meters. I get 7 times 10 to the minus 10 meters. Now that's still a tiny wavelength, but I'm sure you know that that wavelength, that's just a little under a nanometer. Now, atoms are the scale of a tenth, size of an atom, about the size of a tenth of a nanometer, that sort of scale. So this electron's wavelength is comparable, is actually bigger than the size of an atom. So when you think about, in chemistry or whatever, building atoms out of electrons and neutrons and protons, this is saying if you're going to build atoms out of electrons, neutrons, and protons, you better not just be thinking about the building blocks, the electrons, protons, and neutrons, as little particles, because their matter waves, their wavelengths, are as big as the scale of the atoms that you're building. And so this is why wave-like properties of electrons, protons, and neutrons are important in constructing atoms, in constructing the nuclei of atoms. Okay, I want to give you an idea about how matter waves were first observed. So I've said that nobody's seen a basketball matter wave. As far as we know, it's completely impossible, impractical to set up an experiment to see a basketball, soccer ball, football matter wave. But now, about 100 years ago, the detection of electron matter waves was observed. So that was a huge breakthrough, because it's really the proof of this idea that just like light has particle and wave-like properties, matter, like electrons, protons, neutrons, also have particle-like and wave-like properties. And it was due to experiments, the culmination of experiments that were developed by this scientist, Bragg, and then completed by this scientist, Davison. Okay, so Bragg didn't actually detect the electron matter waves. Bragg developed the setup that was used to detect electron matter waves. It was Davison that actually detected electron matter waves using Bragg's setup, Bragg's idea. What Bragg did, which was in itself a big breakthrough, was that he illuminated a crystal with X-rays. So X-rays are short wavelength, high frequency light. So they are way beyond visible light. They have much shorter frequencies, much longer much shorter wavelengths, much higher frequencies than visible light. He illuminated crystals. I don't know, sodium chloride. We've all got sodium chloride at home. We'll illuminate a sodium chloride crystal with X-rays, and he showed through the pattern of the diffraction of the X-rays that the crystal is made of a regular array of sodium chlorine ions. So he's the first one to, we talked about earlier in the class, imagine you could look inside a material and see the arrangement, the lattice arrangement of sodium and chloride ions. It was this experiment, and it was Bragg that was first able to do that, to peer inside a crystal and actually see how the sodium and the chloride ions were arranged in an array or a lattice structure. So it was a big breakthrough. Okay, this is basically how it works. So in this picture here, we've got an incident beam of electrons over here on the left-hand side. So I've got incident beam of X-rays, sorry. There's an incident beam of X-rays, and here's just a couple of X-rays coming in. And over here we've got what I'm calling the diffracted beam of X-rays. So X-rays, we're going to rely on their wave-like properties here. So that's interference and diffraction. And here they're being diffracted from the crystal, and they're going to interfere. And if you want to think about this experiment, think about the soap bubble and the interference of the reflected rays in a soap bubble. In this case, they're diffracted rays rather than reflected rays, but we still get the same sort of interference patterns. So look, here's some X-rays that come in, and they're actually diffracted off this top layer of the sodium iodide crystal, sodium chloride crystal. So that's what you're seeing here. Here's a next layer of the sodium chloride crystal, and some X-rays are being diffracted off that layer. This is just like light being reflected off the outer surface of a soap bubble, light being reflected off the inner surface of the soap bubble. Here it's reflected off the top layer of the ions, here it's reflected off the next layer, plane of the ions. Just like the soap bubble, reflected rays interfere, producing patterns of constructive-destructive interference. The X-rays, diffracted off the two planes of the crystal, interfere with one another. That's a wave-like property, and produce constructive and destructive interference. And it was actually from this pattern of constructive and destructive interference that you can see you could see the layers of ions inside the sodium iodide crystal. And I'm not going to spend any time on it. There's a famous equation called the Bragg law, which tells you the angle of the constructive interference here in terms of the separation between the layers and the wavelength of the X-rays that you're shining on the material. So it's a way that they were able to see the layered structure, the lattice structure inside the sodium iodide crystal for the very first time. And Bragg's law describes that, how that layered structure of the sodium iodide crystal appears in their experiment as they vary the angle of the diffracted light, diffracted X-rays. Well, Davison took that experiment and replaced the X-rays, which have wave-like properties. They undergo diffraction, they undergo interference, and produce the interference pattern of bright and dark fringes. He replaced the X-rays with electrons and directed the electrons into the crystal and looked for patterns of bright and dark fringes of the electrons. Now, at first sight, if electrons are just particles, then that's a completely ridiculous thing to do, because you're firing particles, bullets, electrons, at the crystal, and they're just going to be bouncing off. They're not going to interfere with one another as they bounce off the first layer and the second layer of the crystal. However, if electrons have wave-like properties as well as particle-like properties, then you would see an interference pattern between the electrons through their wave-like properties that are diffracted off the different layers of the crystal and interfere with one another as they emerge from the different layers of the crystal. And so that was Davison's idea, and that's exactly what he did. He shone, now this is a beam of electrons, he shone that onto the sodium chloride crystal, and he looked at the emerging beam, what we would call the diffracted beam. So again, there's electrons that are diffracted off the top layer, the upper plane of the sodium chloride crystal. There's electrons that are diffracted off the next plane of the sodium chloride crystal, and if they've got wave-like properties associated with them, those waves will interfere. The electron waves will actually interfere, and you get constructive and destructive interference. You get bright and dark fringes, and that's exactly what they saw. So they saw it's like seeing the impossible almost. Some French prince has just invented a matter wave in a 3-page dissertation, and Davison runs off to the lab and starts shining electrons, particles, on a piece of sodium chloride crystal, and suddenly he's seeing that they are matter waves. This was a historic moment in physics when suddenly it was realized that something that everybody knew, that electrons, protons, and neutrons were particles, suddenly we realized that electrons, protons, and neutrons are not simply particles. Electrons, protons, and neutrons have wave-like properties associated with them. It was literally, this is the reason for getting a Nobel Prize for this. It really was the moment in which light and matter are synthesized, joined together, unified with a common description. They both exhibit wave and particle-like properties. They are not, at that microscopic level, just completely different objects. They are common objects with common properties. Okay. This is just an example in which I have calculated the wavelength of electron waves, which were used in Davison's experiment. So that's what he used, the electron waves. And I've compared it with the wavelength of light waves, so photons. And I've compared the electron waves and the photon waves, imagining that the electrons have an energy of 10 electron volts kinetic energy, and the photons also have a 10 electron volt kinetic energy. So I just wanted to, we've now reached the point where, we were thinking about photons, and we're thinking about electrons as both having wave and particle-like properties. So I can think about the energy of the photons and the electrons, which is weird for photons, and I can think about the wavelengths of the photons or the light and the electrons, which is weird for electrons. And I'm just going to compare electrons and photons with 10 electron volts. I want to do this because here's where there is an interesting difference. Because what we're going to discover is that a 10 eV electron and a 10 eV photon do actually have very different wavelengths. We'll see these two different numbers here. And the reason for it is that these two particles, whilst they're both exhibiting wave and particle-like properties, they're at opposite ends of kind of a spectrum of what would be non-relativistic, slow-moving particles compared to the speed of light, compared to high velocity, fast-moving particles compared to the speed of light. So a 10 electron volt electron is actually moving at a speed that's much, much smaller than the speed of light. So this 10 electron volt electron is moving at a speed that's small compared to the speed of light. You don't have to worry about relativity for a 10 electron volt electron. 10 electron volt photon, well, sort of by definition, that is moving at the speed of light. So there you do have to worry about relativity when you think about the photons. And when I say we're going to worry about relativity for the photons, we don't need to worry about relativity for the electrons. What I mean is that when we connect, say, the energy and the momentum of a photon or an electron, in one case, that for the electron, we can use the sort of classical non-relativistic expressions for the relationship between the energy and the momentum of the electron. But for the photon, we have to use relativistic expressions for the relationship between the energy and momentum of the photon. So that will be the difference here. So for the 10 electron volt electron, this 10 electron volts is really just kinetic energy, where the kinetic energy is just non-relativistic kinetic energy, 1/2 mv squared, or you can write it in terms of the momentum, p squared over 2m. Okay? So we can do that. We can use this equation for the energy of the electron and relating it to the momentum, because this is a non-relativistic electron. This is the non-relativistic relationship between the momentum and the kinetic energy. When we go down here for the photon, then that equation wouldn't apply. Okay, so here's the relationship between the kinetic energy of the electron and the momentum of the electron. The momentum of the electron, in turn, is related to the wavelength of the matter waves of the 10 eV electron. So I can just replace the momentum by Planck's constant over the wavelength. That's all I've done here. I get this little equation. And then I can rearrange this equation to calculate the wavelength of the 10 eV electron matter waves, knowing the energy, the kinetic energy of those particles. So this equation here for lambda is just a rearranged version of this equation, which was based on non-relativistic equations. And so I rearranged it, and I just plugged in, I won't go through all the details here, you plug in the value of Planck's constant, you plug in the mass of the electron, you plug in the kinetic energy of the electron. You actually also have to plug in the value of c here, 3 times 10 to the 8 meters per second. You find this is the wavelength of these electrons. So these electrons have a wavelength that is a fraction of a nanometer. And these electrons have a wavelength that is the size scale of the layers between the sodium and chloride ions in a sodium chloride crystal. And so you can see electron diffraction on a sodium chloride crystal with 10 eV electrons. Could you see that pattern with 10 eV photons? Actually, you couldn't. And you can't see it with 10 eV photons because of the wavelength. So let's calculate the wavelength of the 10 eV photons. Here we're told the energy of a relativistic particle, it's a photon, it's traveling at the speed of light. That's related to the frequency of the particle through Planck's constant, through this equation here. And in turn, that frequency is related to the wavelength. So I've replaced it by the wavelength. I just fed in the fact that lambda times f equals c here. I plugged that in. And then I've rearranged this equation for an equation for the wavelength. The equation for the wavelength in terms of the energy, this is the relativistic energy of the 10 eV photon. Like this was a relationship between the wavelength of the electron and the kinetic energy, the non-relativistic kinetic energy of the 10 electron volt electron. And then I've just got to plug in the numbers again. I plug in Planck's constant, plug in the speed of light, plug in the energy. This time I get a number that is almost the scale of 1,000 times bigger. So the wavelengths of the photons here are 1,000 times bigger than the wavelengths of the electrons. The wavelengths of the photons are much, much, much bigger than the separations between the layers of the crystal. These photons would be no good at seeing the layers of the crystal in a sodium iodide crystal. It's these electrons, 10 eV electrons, do see the layers, the separate layers of the sodium and chloride ions inside the sodium iodide crystal. Sodium chloride crystal. Okay, I want to finally conclude just a few remarks on wave. So we talked about matter having both particle-like and wave-like properties, and light having both particle-like and wave-like properties. We call this wave-particle duality. So light has dual properties that are wave-like, particle-like, and matter has dual properties that are particle-like and wave-like. I wrote down here, and I was careful when I wrote this down. I wanted to write down a statement that summarizes that. This word here, electrons, this could be, I could replace this with photons or light also, but I just picked electrons. I say that electrons sometimes behave as if waves and sometimes behave as if particles. So why did I write it like that? So I wrote it like that because I wrote sometimes behave as particles, sometimes behave as waves, because electrons or photons don't simultaneously, they don't simultaneously behave like a wave and a particle. They just, if you were doing an experiment with electrons, you're doing an experiment with photons, you would sometimes see them behave like a wave, and at other times see them behave like a particle. So think of that diffraction experiment. When the electrons are diffracted off the crystal and the electrons are interfering with one another, they're behaving like waves. But when the electrons are counted, detected, observed by Davison, they're behaving like particles. He's counting the electrons. So in one part of the experiment, they were governed by their wave-like properties as they diffracted and interfered. In another part of the experiment, they were governed by their particle-like properties as they were counted and observed. So I want to be clear that in wave-particle duality of light and matter is that you sometimes observe one property, wave-like, or other times you observe the other property, particle-like, not simultaneously. The other point about this sentence is I put in as if waves, as if particles. Why did I do that? So that's actually a very important point. Electrons act as if waves and as if particles sometimes. Light acts as if waves, as if particles sometimes. But light and electrons are actually neither, right? Light, the notion of waves, the notion of particles is our everyday conception of the things around us. Things are either particles or waves. But it seems that at the microscopic level, for electrons, for photons, they are actually neither particles nor waves. There's something that we don't experience in our everyday world. They are actually objects that we don't experience in our everyday world that can sometimes act like a wave or sometimes act like a particle. So the notion that we can conceive of electrons as particles or waves, or light as particles and waves, is making dangerously familiar, I would say, or misleadingly familiar, the idea that we know what an electron looks like, we know what a photon looks like, because it's really not either a wave or a particle, is something different. It's something completely different. There's something completely different that can exhibit wave-like and particle-like properties. And so that's why I said as if. Okay, I got a quiz here. Okay, this is just a question about de Broglie waves, about matter waves, where we have an everyday object. It's an object that has a large mass. It's a truck. It's an object that has an everyday speed. It's 30 miles per hour. And the question is simply, sort of, can we observe the matter waves? And if we can observe the matter waves, are they observable, or are they unobservable because the matter waves are too long for us to observe or too short for us to observe? Okay, I'll get going again. This example of the moving truck and its matter waves are just like the examples of the basketball, soccer ball, football. The basketball, soccer ball, football, everyday objects with everyday speeds and everyday masses are unobservably small. They're way, way too small for us ever to observe, ever to imagine observing. The same is true for the truck. This truck that is even heavier than a basketball or football or soccer ball, obviously. It's the same speed scale as a basketball, football, or soccer ball. It has a much, much bigger momentum as a basketball, football, or soccer ball. It has a wavelength. A matter wave wavelength of the truck is even shorter, is even smaller than the matter waves of the basketball, the football, or the soccer ball. So we would never, ever, ever imagine observing it. It's only in the subatomic world, the world of atoms and molecules, of electrons, protons, and neutrons, that we observe these matter waves, and that these matter waves are important. Okay. So the idea that electrons, protons, and neutrons have wave-like properties, and the idea that light, X-rays, infrared have particle-like properties is a radical idea. It changes our conception of matter and light, but it also has some enormous consequences that are both physical and sort of philosophical. Yeah. I can never say that word, so I don't want to say it. So the consequences of wave-particle duality, and we're going to see this, is that wave-particle duality, when it was understood, became kind of this tipping point, or this turning point, which forced scientists to accept that a notion of classical physics, that is, that physics is kind of deterministic. You could always, in principle, predict exactly what's going to happen. In quantum physics, physics isn't completely deterministic. You can't predict exactly what's going to happen. In classical physics, in principle, you could measure observables, all the observables of everything to ultimate precision. In quantum physics, there's a limit on your ability to measure the observables of things to a certain precision. And this all came out of, this all emerged from wave-particle duality. And this is all the foundation of the mathematical theories of quantum physics. So we're not going to go a lot into mathematical theories of quantum physics. We'll build an atom in the final class, but we won't go into the full mathematics of quantum theory. But it's founded on the notion of wave-particle duality. So that's the key to it. And it's founded on this notion that emerges from wave-particle duality, which is that we're not living in a deterministic sort of clockwork classical world. We're living in an indeterministic, probabilistic quantum world. And so that was a fundamental change that some of the scientists at the time just, refused to accept. And some did accept that we're living in this indeterministic, probabilistic world. Okay. And as I say, this conclusion comes out of the notion of wave-particle duality of matter and light. And to introduce it, I want to discuss a kind of a foundation of it that is present just in waves themselves. So this slide and the next slide are just about waves. They're just about classical waves. So they could be sound waves, they could be ocean waves, they could be light waves, what I'm going to discuss now. And so we're just going to discuss some features of waves, specifically about your ability to know the wavelength of a wave and the location of a wave. Simple question like that. And then, once we've discussed our ability to know the wavelength of a wave and a wavelength of a wave based on our classical picture of waves, we'll add to it the fact that, well, waves for electrons and photons, for matter and light at microscopic levels, also have these dual particle-like properties. And what are the consequences there? So we'll add wave-particle duality to this understanding about ability to know a wave's wavelength, ability to know a wave's location. On this slide, I've got two pictures. On the right, didn't buy enough pixels on either of them, but and this is the left, by the way. On the left, what you're asked to imagine from this picture is that this is this smooth pond, and rolling gradually across this pond is these gentle waves that are just streaming across the pond. And then over here on the right-hand side, this is a really interesting wave. You sometimes see these. It's a superposition of waves, actually. And it's a wave at a very localized point. And I just want to talk about these two extremes here. So supposing, let's step over to the left-hand side. We've gone to the park, and we're looking at the pond. And we ask ourselves the question, what is the wavelength of this wave, and what is the position of this wave? So those two questions about a wave that we could ask. What's the wavelength? What's the position? Well, regarding the wavelength, I could tell you the wavelength, right? These are regular ripples of waves. They are what we call technically plane waves. the separation between crests is regular. The separation between troughs of the wave is regular. I could measure the number of centimeters between consecutive troughs. I could measure the centimeters between consecutive crests, and I could tell you the wavelength. So I could tell you that really rather well. But you ask me, well, where is this wave? Well, I mean, I can't point to a place where this wave is. It's just in this enormous pond. So I can't really tell you where the wave is. I can tell you the wavelength very accurately, relatively accurately, but I can't tell you where the wave is. So we can know the wavelength in this example, but we can't know the wave's location. It's just spread out all over the place. The reverse is true here. So we're at the ocean and we see wow, that looks interesting. I asked the question, what is the position of this wave? What is the wavelength of this wave? Well, in this case, we could point to the position, right? It's right here. This is where that wave is. We can say exactly where that wave is, completely different from the pond, but we couldn't answer the wavelength. We couldn't count the number of centimeters between crests and crests or troughs and troughs and determine pretty accurately the wavelength. This is, in fact, I'm going to just tell you this wave here that is localized in space, concentrated in space, is actually the superposition of a whole range of wavelengths. So you could never know the wavelength because it's just a whole range of wavelengths. And so this is the other extreme example with waves, is that if you know the position of the wave, or this might be called a wavelet, if you know the position of the wave, then you can't know the wavelength. And so there's two extremes here depicted in these two little cartoons. This cartoon, we can know the wavelength well, but we don't know the position. This cartoon, we can know the position of the wavelength well, but we don't know the wavelength. So there's actually, for waves, and this is just everyday waves, I'm not getting quantum here, for just everyday waves like water waves, sound waves, any other light waves, right? There's sort of an interesting relationship between how much you're able to know the position of the wave, that's what I called the delta x over here, how much you're able to know the wavelength of the wave. So a typical waving structure is actually a superposition of lots of different plane waves, lots of different fixed wavelength, fixed frequency waves. So that's what I'm picturing here. We're imagining a structure that's made out of many different waves. That means that it has a spread in wavelengths. So I'm picturing the spreading wavelengths of these different guys over here on the left. That's the delta lambda, the spreading wavelengths. I'm picturing the localization, the spread in position of the wave with this delta x here. So when I add these waves together, I get this kind of pattern here. I'm not asking you to do this. I'm just explaining that this is how we imagine a little wavelet as being built up of many different frequency or wavelengths that cause it to be distributed in some region of space and have some spread in wavelengths. Now, the point is that if you concentrate the wavelet in a smaller region of space, if we make delta x smaller, you make the spread in wavelengths larger. If you let this wavelet spread out in space, then you need a smaller range in wavelengths. You make this side smaller. And that's exactly what we saw in the last pair of pictures. They were the extremes of this cartoon here. In one extreme, that calming pond with the waves just rippling across the surface, the wave was spread out enormously. Delta x was large, but the wavelengths, well, it was a very well-defined wavelength, so this would be very narrow. And then that other, not so calming, this collision of these waves in the ocean with this big spike of a wave, that's the other extreme. In that case, the spread in the spatial spread in the wave was very narrow, so delta x would be small, but it was made up of a huge range of wavelengths. And so with waves, and there's nothing quantum here, but just with waves, if you know the position of the wave well, it must be that it's a whole range of wavelengths. You don't know the wavelength very well. So well-known position is poorly known wavelength, and vice versa. If you know the wavelength well, you determine the wavelength well, you don't know the position of the wave well. It's spread out in space. And that's a feature of water waves, sound waves, and light waves. Okay. So there's nothing we could have done. We could have written all this down 200 years ago about waves. There's nothing. This is all classical stuff. There's nothing quantum stuff here. But now we're going to add to it wave-particle duality. We're going to add to it the new quantum stuff, and we're going to see the conclusion. So the point is that this spread in wavelength is related to a spread in momentum through de Broglie's equation, right? If in de Broglie's equation, which is that the wavelength is equal, of the matter wave is equal to the Planck's constant divided by the momentum of the matter wave, if the wavelength has a spread in it, it means that there's a corresponding spread in the momentum. So when you add wave-particle duality to this feature of waves, what you discover is that you can't simultaneously know the position of a particle. So now we're thinking about the particle-like viewpoint. We can't simultaneously know the position of a particle and the momentum of the particle. So this is the remarkable bit of the conclusion. There's nothing remarkable about you can't know the wavelength and the position of a wave simultaneously. But now when you build in wave-particle duality and you connect the particle-like properties with the wave-like properties, now you can't know the position and the momentum of a particle simultaneously. And that's completely at odds with classical notions, right? If you think of the basketball in 211, right? Nobody would say that, well, you can't know simultaneously the momentum of that basketball and the position of that basketball. We always assumed, actually, you could simultaneously know the position and momentum of a basketball. If we're thinking about a truck in Physics 211, right? Physics 211, you wouldn't have thought, well, you can't, look, stop. You can't know the momentum of the truck and the position of the truck simultaneously. Don't go on with this problem. We would never have said that. So this notion that you can't simultaneously know the momentum and the position of a particle, that is a consequence, a direct consequence of wave-particle duality, is something that is unheard of in classical physics and is a key new feature in quantum physics, and is the basis for all the mathematical structure, all the mathematical framework of quantum physics, of matter waves and photons and so forth. So just to quantify this fact, this new fact that you can't know the position and momentum of a particle, there's some limit on your ability to know the position and momentum of a particle, is what's called an uncertainty relationship. So I wrote it so big here to make it so important, it's almost too big to read. At least it is for me. So this is the uncertainty principle. It's called the uncertainty principle. It's due to a scientist called Heisenberg. It's a consequence of the wave-particle duality. It's a direct consequence of wave-particle duality, that waves with wavelengths and they're delocalized also have particle-like properties like momentum and energy. And it simply says that you can't, there's a limit on how well we can know the position of a particle and the momentum of a particle. So let me explain that. So there's two sides to this equation, but it's not an equal sign. Notice that. It's greater or equal than is in here. So this is not an equal sign. It's greater than or equal than. So the left-hand side has to be at least the size of the right-hand side or bigger. So that's the first thing. On the left-hand side, there's a delta x and there's a delta p. Who's the delta x and who's the delta p? Delta x, that's the notation for the uncertainty in the position. That's how well you can know the position. So you could know the position to a millimeter, or you could know it to a nanometer, or you can know it to a whatever meter. That's the uncertainty in the position. The delta P is the uncertainty in the momentum. So you could know the momentum to, I don't know, 1,000 kilogram meters per second, or 10 kilogram meters per second, or 0.1 kilogram meters per second. That's how well you can know the momentum. And so this equation says if you multiply these two uncertainties about how well you could know position and momentum, it has to be bigger than a scale that's set by Planck's constant. This is Planck's constant over 4 pi. We don't need to explain the 4 pi, but it's Planck's constant over 4 pi. And so again, Planck's constant is set in the scale, not just a wave-particle duality, but this sort of indeterministic versus deterministic nature of quantum versus classical universes. So Planck's constant defines a limit on how well you can know position and momentum. A couple of extremes are, right, if you knew the position really, 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 really well, then you wouldn't be able to know the momentum. You'd be really uncertain about the momentum. So that's one extreme. And then another extreme would be, you know the momentum really, 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 really well, then you couldn't know the position. So that latter case is like the calm pond with the ripples of water running across the pond. We could know the wavelength really well, which is by wave-particle duality, the momentum, but we can't know the position really well. And then the other extreme, where you know the position really well, is like that little spike of a wave in the ocean. It's called a soliton. It's a very special event. You know the position of that wave really well, but you can't know the wavelengths that it's built out of. You can't know the momentum through wave-particle duality that is built out of. And so this is the sort of, in a way, this is the crown jewel of wave-particle duality. This prediction that there's a limit to a limit to your ability to know things, like position and momentum for particles. So just to stress that, in classical physics, there is no such limit, right? In 211, there was, when we talked about particles moving, there was no limit on how well we could exactly know their position and their momentum, their position and their velocity, for example. In quantum physics, there is a limit that's set by Planck's constant. Theoretically, you can't simultaneously know the position and the momentum of a quantum particle like an electron or a proton or a photon or whatever. The trouble is, what happens if you try to know one, if you try to know the position, say, you're going to blur the other one. You won't know the momentum. And if you try to know the other one, you try to know the momentum, you're going to blur the other variable, the position. So whatever effort you try, so it's sort of, I don't know, you squeeze it here and it pops out over here. So it's, you try and measure one thing and you're going to disturb the other thing. Try and measure the position, you're going to disturb the momentum. Try and measure the momentum precisely, you're going to disturb the position. You can't get around it. There's no way around it. Here's just to end on, a quick example. So now you're worried, I spent, a whole semester in Physics 211, and now all that stuff about, basketballs and trucks, you can't measure their position and momentum. Do I need to worry about that? No, you don't need to worry about that, but let's check it. 2 kilogram object has a position uncertainty of 0.1 of a millimeter, so a tenth of a millimeter, part in 10 to the 4 of a meter. What's the minimum uncertainty in the object speed, according to uncertainty principle? What we'll calculate is the uncertainty in the object's momentum from the uncertainty principle, and then we'll calculate the corresponding uncertainty in the speed. So this is a case of using the uncertainty principle. Here's the uncertainty principle, uncertainty in position, uncertainty in momentum. Their product is of the order of Planck's constant, more specifically, Planck's constant divided by 4 pi. We always do rough calculations with uncertainty principle. Delta P If we want the uncertainty and the momentum of this object, this everyday object, all we've got to do is divide the right-hand side here by the uncertainty in the position, which is something we know. So this is the 10th of a millimeter. Plug in the numbers. Planck's constant, 10th of a millimeter, the uncertainty position. This is the uncertainty in the momentum of this particular object. If I want the corresponding uncertainty in the velocity, I just need to use the relationship between momentum and velocity. It's this one here. It says the momentum equals mass times the velocity. It also implies that the uncertainty momentum is the mass times the uncertainty in velocity. I want the uncertainty in velocity, so I can just divide, rearranging this equation, the uncertainty in momentum by the mass. If I do this, this is the uncertainty in the speed. You see, it's just unobservable again. It's an unobservably small effect in our everyday worlds.